Alright, in this video we're going to talk about the standard heat of formation as well as how to calculate the standard heat or energy of a reaction. Heat of formation can also be called the energy of formation or the enthalpy of formation. It all equates to delta H. And it's defined as how much energy, the change in energy to form a mole of a specific compound from its elements. And we'll come back to that in a second. This little 0 or O, if you want, is called knots, and it means at standard conditions. So specifically, this is the energy associated with performing this reaction at 298 Kelvin in 1 atmosphere. And we're not ever going to change conditions, but standard conditions, that's where it's coming from. In this class, we won't change the conditions. These are constant values. The heats of formation are something that you can find online. We're going to use a page out of our textbook actually. But where they come from is from adding up the bond energies from breaking and reforming individual bonds for that specific reaction. And one thing to keep in mind is as you're using these reference tables to find these heats of formation, if you're looking for a specific element as opposed to a compound, it's 0 because it's defined as the change in energy to form a compound. So if it's not a compound, if it's an element including diatomics, the delta H sub F is 0. You won't find it in the reference table. So what does this mean as far as breaking up the bond energies? Let's just use our standard water equation. If we're making water and we balance it, oxygen, if we were to draw it out as O2, actually has a double bond, which means that it's sharing multiple electrons in this bond. We'll come back to this when we talk about our unit on bonding. So we have one oxygen molecule and we have 2 hydrogen molecules, which are only single bonded together. And they react to form our 2 water molecules. So to calculate the standard heat of formation to form 1 mole of water, it's to form one of these, and it's how much energy it takes to break these bonds as well as these bonds, and then how much energy is given off when these bonds are made. And you add all of those up, and that's how you come up with your standard heats of formation. You could do all that individually, but thankfully there are tables for that as well. So we're going to use this equation to calculate our standard heat of reaction. Here, let's turn the webcam on in case you actually want to look at me. Where did I go? Now this standard heat of reaction is a theoretical calculation, and this is what's often used when comparing lab results. So if you had the experimental heat of reaction, if you had calculated that, you would compare this to your standard heat of reaction. And obviously you would need to adjust if you weren't at standard conditions, but it would give you some idea of what your percent error was in that particular lab. So it's how much energy is the change in energy for that specific reaction. So let's look at this equation for a second. It looks complicated, but it's really not. I'll give an example on the next page. Delta H is our change in energy, or the change in enthalpy, or the change in heat for a specific reaction. This capital letter E is a Greek symbol. It means sum of or add all together. N is moles times the individual heats of formation of the products of the reactants minus adding all up the moles times the change in heat of formation for the reactants. So, oops, I didn't want to do that. one thing that I should have highlighted better in this slide is that ultimately this equation will tell us whether something is exothermic or endothermic. Once you've performed this calculation, if you end up with a negative delta H, it means it's an exothermic reaction. The temperature should go up. If it's positive delta H, it's an endothermic reaction. So let's do one. So given the following reaction and the standard energies of formation or enthalpies of formation right here, calculate the standard energy or enthalpy or heat of reaction to determine if the reaction is endothermic or exothermic. So this is really a two-part problem. You have to do the calculation involved, but then you also have to answer this question. So we're going to use this equation, and here's our chemical reaction. And just as a reminder, the products are on the right-hand side and the reactants are on the left-hand side. So when we do this out, our delta H of reaction equals, and I recommend using square brackets here and lots of parentheses, otherwise you end up with math errors due to the negative number. It's the summation of the moles times each of the individual enthalpies of formation of the product. So we're going to start on this side. We have 2 moles times the value of water, which is minus 242. And summation means add together. So we're going to add that to 1 mole of CO2, but we want the heat of formation, which is minus 393.5. And those are our only products, so now we're done adding them up together, subtracted by doing essentially the same thing on the reactant side. So we have 1 mole of methane, the value being minus 74.8, plus 2 moles of oxygen. Now in this, I've told you that the standard enthalpy of formation for oxygen is 0. But if you were to use your reference tables, it wouldn't be listed there because oxygen is a pure element, so there's no energy change associated with forming it. It exists in our atmosphere. So we are going to multiply 2 times 0, which is 0, thankfully. But we'll write that down. So now it's really just a math problem. But this is where many students make mistakes because we're going to ultimately subtract probably a negative number as well as we're adding negative numbers. So just be very careful as you're doing all of this math out. We have 2 times negative 242, which is minus 484, plus negative 393.5, all subtracted by, it's negative 74.8. Plus 2 times 0 is 0. So to simplify this even further, we have minus 877.5 minus negative 74.8. That's a decimal spot. So see how we're subtracting a negative number here? That almost always happens. So minus 877.5 plus 74.8. You end up with a delta H of reaction of 802.7, and your units are kilojoules per mole. So now we need to answer the ultimate question: is this endothermic or exothermic? And that all boils down to this sign. Since it's a negative sign, it is an exothermic reaction. And that's it for this video today.